Hello students, welcome back to our class. So today we are going to see Lenz's law. In electromagnetic induction, we have already studied how to produce EMF or how EMF will be induced in a circuit when we change flux. Okay, so EMF is nothing but a rate of change in flux. EMF is equal to rate of change in flux. Already we have seen in the very first session. So induced EMF E is equal to minus d phi by dt, or this is actually instantaneous. So average EMF is change in flux divided by the time duration for the change in flux. Right, what is this flux phi? Phi is equal to B dot A, or we can say that BA cos theta. BA cos theta. Magnetic field, area vector. Then what is theta? Theta is the angle between magnetic field vector and area vector. Right, so this much we have seen. What is this negative? This negative indicates the direction. So we were not too much worried about the direction in the previous session. Completely we were concentrating on finding the magnitude of flux induced EMF. Okay, today we are completely concentrating on how to find the direction. So this was found by a scientist called Lenz. So today we will be seeing Lenz's law. Lenz's law. So Lenz's law gives the direction of induced current. If the induced EMF, if that circuit, if we close, okay, then current will pass. If it is kept open, EMF will be induced, but there won't be any current. If we connect it or if we switch on it, then if it is a closed circuit, current will pass. So that direction of induced current we will find using Lenz's law. Now, according to Lenz's law, the direction of induced EMF, is such that it opposes the cause producing it. Whatever is making this change or whatever is changing, this induced EMF is trying to oppose that change. If magnetic field is increasing, induced EMF will be made in such a way that, or induced EMF will be formed in such a way that will try to decrease the magnetic field. Suppose if magnetic field is decreasing, then this induced EMF direction will be in such a way that it will try to increase the magnetic field. So that is how it will try to oppose the cause producing it. Another point is, it is based on the conservation of energy. It is based on the conservation of energy. This Lenz's law is valid and it completely obeys the conservation of energy concept. Or because some energy will be converted into another energy always. It is neither created, right? So, or nor destroyed. So same way, some energy will be converted into another energy. So here we have seen in the first session that a coil will be moving, magnet will be moving, switch will be on and off. Okay, some mechanical work is done. So that mechanical work will be converted into electrical work. So that is what is actually happening here. So based on the conservation of energy, this Lenz's law works, or Lenz's law completely, okay, explains the conservation of energy in this context. Okay, now the statement of Lenz's law is the polarity of induced EMF is such that it tends to produce a current. Okay, if we make the circuit a closed one, it will produce a current which opposes the change in magnetic flux that produced it. Okay, so some change in magnetic flux is what is producing this EMF. This EMF will be trying to oppose this change in magnetic flux. Okay, because of change in magnetic flux only EMF is producing, but that EMF will try to oppose that change. Clear? So here this much is the theory which we need to discuss. Now we will take case by case. All those cases are actually problems. Okay, so case by cases we will be discussing. They are actually problems only, but we will segregate the different types of concepts, okay, based on problems or based on the cases in Lenz's law, right? So here all right, okay, right, fine. We'll directly get into the cases, and one by one we will sort it out, how to solve it, right? Fine. Okay, students, this is first case. Magnetic field direction is given and magnetic field is increasing. Throughout this session, the question is direction of induced EMF in coil. Okay, direction of induced EMF in the coil. This is what we are going to see throughout this session. So every time I will not be writing this. Okay, question is understood. Okay, so the simple concept, okay, it is easy for us to think if you understand in this way. In Tamil, okay, kada solvangalla, kadai. Okay, some people will come and they will say oru veetla oru amma irundanga, oru maganum irundanga. Okay, so amma vandu magan நல்ல சந்தோஷமாக இருந்துச்சுன்னா அம்மா திட்ட ஆரம்பிப்பாங்க. ஓகே, அம்மா வில் பி ஸ்கால்டிங் த சன். மகன் வந்து ரொம்ப வருத்தப்பட்டு அம்மா திட்டிகிட்டு இருக்கிறாங்கன்னு சொல்லிட்டு ரொம்ப வருத்தப்பட்டு அழுது ஒரு லெவலுக்கு கீழே போகும்போது அம்மா என்ன சொல்ல ஆரம்பிப்பாங்க, அம்மா வந்து அவன்கிட்ட நல்ல பாசமாக நேசமாக, ஓகே, தமாசெல்லாம் சொல்லி நல்லபடியாக சந்தோஷப்படுத்துறதுக்கு ட்ரை பண்ணுவாங்க. ஓகே, சரி, அவன் சந்தோஷப்பட்டு விளையாடி எல்லாம் வரும்போது, சரி, கொஞ்சம் அவன் திமிரெல்லாம் காமிக்க ஆரம்பிக்கும் போது அம்மா மறுபடியும் திட்ட ஆரம்பிப்பாங்க. ஓகே, ஸோ சந்தோஷமாக இருக்கிறது பார்த்தீங்கன்னா அம்மா வில் டூ திட்டல். சங்கடமாக இருக்கிறது பார்த்தீங்கன்னா அம்மா வில் என்ன புகழ்ந்து பேச ஆரம்பிப்பாங்க. ஓகே, just for understanding I am telling the story. Okay, so those who don't understand Tamil, I am telling you, one mother and son was there. Okay, suppose if the son is too happy and excited, okay, he has roamed with friends and came back home. If he is too much excited, amma will start scolding him like anything. Okay, summer scolding, too much scolding. So it will spoil that fellow's mood. He will start moving into mood off. It will take him such a way that he will go to depression level. Okay, then whole day will be lost for him. Then he won't eat and சாப்பிட மாட்டாங்க. Okay, he will show all the symptoms of depression. Then finally amma will realize that okay, my son has gone beyond a level. Then amma will start praising him. You have got so much talents, you are very handsome, your character is so superb, and she will start motivating him in such a way that he will go to again another ecstasy. Okay, he will go to excitement, and excitement is too much means amma will scold. Same kind of character we can see here also. Okay, just for fun I was relating this example with the concept. Okay, always discussing the subject. Okay, these kind of talks will come a lot if we are in the offline class, direct classes. Seeing the faces of the students, definitely we will feel to talk something. Okay, but since I am not able to see you, it is another problem, right? So most of the time our discussion is 99% of the time we discuss only subjects. So just for a change of mood I said that example. Okay, so magan or son, excitement, amma will scold. Magan, son, too much depression, amma will start motivating. Okay, no, this is how actually, not amma, not mothers, actually generally socially this used to happen. Same way here, same concept can be applied here. We will get all the answers correctly. Now I will tell you how to approach these kind of problems. Okay, this is one type. The thing is, they are saying B is increasing, that is magnetic field is increasing. What is the direction of magnetic field? Cross is given. Cross is given means it is going inside. Going inside, cross. Okay, going inside, cross means it is going inside. Okay, dot, this is not vector and dot, just showing the direction. Okay, coming out, coming out. Okay, now cross magnetic field, that is the magnetic field which is going inside, is increasing. So if the magnetic field increasing, flux will change, EMF will be induced in this coil, current will induce in the coil. So in the question, cross magnetic field is increasing. So what it will do? It will try to, he is happy now. Now we need to demotivate him. Cross magnetic field should decrease. So to decrease cross magnetic field, what we should do? We should increase dot magnetic field. Dot magnetic field means this is cross magnetic field. Dot magnetic field means this direction. This fingers will show the direction of current. So I can show like this is the direction of current. Okay, so dot magnetic field which is coming out, I need to increase. So in order to increase dot magnetic field, in what direction current should go? Current should run in this direction, so that dot magnetic field will increase. So anti-clockwise current will be induced in the coil. Clear? This is the concept. So same kind of problem, increasing cross, decreasing dot, decreasing cross, all these things we will see. Okay, note it down. Yeah. So next question. So what is the direction of induced current in this coil? Okay, so you can pause the video, try yourself. Okay, you will get the answer. Right, then now we will verify. Okay, done. Okay, shall I do? Now dot magnetic field is decreasing. Dot magnetic field is decreasing. Okay, so dot magnetic field is in sad mood. Romba manavaliyoda, he is sitting with so emotional mood. Okay, he is very sad. Now we need to motivate him. Okay, so what we should do, right? So thing is, dot magnetic field is decreasing. Now what we need to do? We need to increase the dot magnetic field. So to increase the dot magnetic field direction is what? Towards us. This is dot magnetic field. Cross means this one. This is dot. Dot means this direction, magnetic field. So current will be in which direction? Wherever I am showing fingers, in which direction I am showing fingers, this will be the direction of induced current. So this is going to be anti-clockwise again. Okay, correct? Okay, so whatever is happening here, we need to oppose it. Okay, that is the concept. Okay, now another question. A conductor, okay, a conductor carrying current. Conductor carrying current, in which direction? Upward direction current is moving, and current is increasing. Current is increasing. So if the current is increasing, then what will be the direction of magnetic field here? Current is increasing, right hand thumb rule, current is going like this side, magnetic field will be coming out. Okay, this side magnetic field is coming out. So likewise, if we come to this direction, magnetic field is going in. So here we can say that magnetic field is going in. Okay, so this is the direction of magnetic field. So I is increasing means the cross magnetic field is doing what? That is also increasing. So what we need to do? We need to decrease the cross magnetic field due to this. So this cross magnetic field should decrease. So what we should make? We should increase dot magnetic field. In order to make a dot magnetic field that is coming out, that the current direction should be like this. So this will be the current direction, which is nothing but anti-clockwise. Clear? Okay, that is the direction of current. Whatever is happening there, exactly opposite we should create here. For that, what should be the direction of induced current? That is a simple concept. So another question. Here current is coming in this direction and current decreases. Current is decreasing. Okay. So this is the direction of current. So if this is the direction of current, see right hand thumb rule, where this fingers are curling, that will be the direction of magnetic field. So if the current is coming like this, the magnetic field at this point, at this or through this board, what will happen? It will be going inside. Okay, so cross magnetic field. Cross magnetic field. So what is happening here? Cross magnetic field is decreasing. We need to increase the cross magnetic field. So to increase cross magnetic field means one which is going inside. So this is the direction of magnetic field that should come, that should increase. So what should be the direction of current? Clockwise, or this should be the direction of current. Okay, so clockwise. Clear? That should be the direction of induced current. Okay, another question. So here in this coil, current decreases. Okay, current is moving in this direction and current decreases also. So when current decreases, what will happen? Okay, so when current is moving in this direction, okay, current is moving in this direction, what should be the direction of magnetic field? What should be the direction of magnetic field? I mean for this coil, with respect to this coil. So current will be moving like this, outside magnetic field will be inside. Okay, but inside this circular coil, magnetic field will be coming out. Correct? Magnetic field will be coming out. So dot, 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 dot. Okay, so when current is decreasing, dot magnetic field is also decreasing. What we need to do? We need to increase the dot magnetic field. So to increase the dot magnetic field here, to increase the dot magnetic, what is the direction of dot magnetic field? Outside. So if this is to happen, then definitely the current direction must be which direction? This way. Correct? So this is what? Anti-clockwise. Anti-clockwise current. Another question. Same model. Current is moving in this direction in this coil and current value increases. This current value increases. So when current is moving like this, then in this part of the system, okay, what will be the direction of magnetic field? The direction of magnetic field will be outside. It will be coming out. Okay, right. So what will be the direction of current, induced current in this coil? So here current increases, so the corresponding magnetic field, which is dot magnetic field, that also will be increasing. We need to decrease dot magnetic field. So to decrease dot magnetic field, we need to increase cross magnetic field. Cross magnetic field means once that is going inside. So inside means what should be the direction of current? This should be the direction of current. So I am marking that. So we need to make a clockwise current, so that the magnetic field will be made here cross. So cross magnetic field will be increased here. Clear? So whatever be the situation, whatever is increasing, we should decrease it. Whatever is decreasing, we should increase it. Okay, that is how its behavior is. So till now we have seen the dot magnetic field increasing, cross magnetic field decreasing or increasing, those kind of things. Now again magnetic field will be coming, but a little bit change in the pattern of question. This is another type of cases which we can see in Lenz's law. This is a magnet, bar magnet, and this is a coil. North pole, south pole. This is coming towards this coil. This is coming towards this coil. This was the first experiment we have seen in this chapter in the beginning. So this bar magnet is coming towards it. Definitely an EMF will be induced in this coil. Current will be flowing in this coil. So what will be the direction of current? The same question only throughout this topic, same question. What will be the current that is induced in this coil? Okay. So pause the screen, try yourself. Okay, make a try, then verify the answer. Clear? Now see. Suppose if we keep a bar magnet, okay, if this is north, if this is south, what will happen? From north pole, okay, magnetic field lines will emerge and it will be reaching the south pole. Correct? Okay, so from north pole it will emerge and it will join at the south pole. Now from north pole it will emerge and it will meet at the south pole. Inside the magnet, the lines will be moving. The magnetic field lines will. So inside a bar magnet, from south pole to north pole, magnetic field lines will be moving. Outside, from north pole to south pole. So in moving charges and magnetism, the direction of electric current and its associated magnetic fields current, okay, and in a bar magnet, how magnetic field lines are moving, all these things we know. Now let's look here. Suppose if the current is moving in clockwise direction, so this is clockwise direction when we look from here. If we are looking from the other side, it will be anti-clockwise. Okay, see here it is rotating like this, current is moving like this. From this side, this is anti-clockwise. For other side, this is going to be clockwise. So that is why we have shown an eye here. So from looking from this side, okay. Now come back to this. So if the current is clockwise, this is the direction of current, these fingers. So direction of current, where this thumb is showing inside, means magnetic field is going inside. Magnetic field is going inside. Now take this magnet and keep it in this plane. In which way? South pole we will keep it here, north pole we will keep it there. So see, if we take this magnet and if we keep here south pole, so to south pole magnetic field is going inside. So to south pole magnetic field will be going inside. This direction, if I show here, this is going to be like this, same. So where current is running in clockwise direction, that end will be acting as what? South pole. So that is why we will be showing a sign like this, south, S. So south pole clockwise, magnetic field will be going inside. Now here, suppose if we take anti-clockwise direction looking from here. Anti-clockwise direction looking from here. So anti-clockwise direction, if we keep these fingers, where this thumb is showing? Thumb is showing outwards. Outwards means outward magnetic field it is showing. Now, if we take this end of the bar magnet, if we keep it here, okay, I take bar magnet, if I make a hole here, patak, if I keep it inside, this is going to be north pole. Magnetic field lines are coming out, so I can show like this, coming out. Okay, so what is this actually? This is, okay, north pole. This is north pole. Okay, so south pole, north pole. So anti-clockwise. So if we look at an end, look from one end of a coil, if it is the current is moving in anti-clockwise direction, we should infer that will be acting as north pole. If the current direction is clockwise, then that end will be acting as what? South pole. Okay, so clockwise south pole, anti-clockwise north pole. Need not by heart it from the concept. Okay, by looking at the direction of current, direction of magnetic field, okay, direction of magnetic field, direction of current, you will be able to find it easily. Okay, right. So this basics is must. This is the prerequisite for understanding this, for dealing these kind of questions, right? Okay, just note it down, right? So shall I erase this? Completely note it down. Pause the screen, note it down. Done? Okay, right. Now our phenomenon, north pole is coming. North pole is coming. Now what this guy will be thinking? North pole should not come. North pole should not come. Okay, so he should make what? If he makes here north pole will repel north pole. So if north pole is coming, what he should do? He should make here north pole. In order to make north pole, what should be the direction of current? Direction of current should be anti-clockwise. So this is how. Anti-clockwise means this is how. Okay, simply I am writing anti-clockwise. So if we are just the vision, from the vision, if you feel like this coil is this side or this coil is this side, that can vary. Simply I am telling like of looking from this side, this current should be anti-clockwise. Okay, clear? So north pole is coming, this should make north pole so that it will repel. That is the answer for this kind of question. Okay. Okay, another question. South pole is coming in this direction. South pole is coming here. So south pole is coming towards it. It doesn't want south pole to come. So this wants to repel. So to repel, we should make here south pole. In order to make south pole, what should be the current here? Current should go in anti-clockwise. Okay, so or I am writing this as clockwise. Clear? Okay, so here a bar magnet is falling, it is coming down. So what should be the direction of current here? So north pole is coming. What we should make here? We should make here north pole. So north pole means what is the direction of current? Anti-clockwise. Okay, so anti-clockwise. Clear? So here a bar magnet is falling, coil is here, so this is moving away. Okay, so for this coil, this south pole is moving away from it. Now this is moving away, so now this wants this back. Okay, so it wants to attract that south pole. If it is coming, repulsion. If it is moving away, it is attraction. So what we should make here in order to attract south pole, we should make north pole. Okay, so if we make it north pole, it will attract this. So if north pole means what kind of current? Anti-clockwise current. So if this is clockwise, we can write this is anti-clockwise. Okay, so anti-clockwise current will be formed there. Okay, so a bar magnet south north, so it is moving away. So north pole is moving away from this. So this will make what? This will make south pole. So in order to make south pole, so this wants to make south pole to attract this. South pole means clockwise. Clockwise. Clear? Okay, see this question. Magnetic field. Okay, constant. Okay, this is constant. Okay, B is constant. A loop is entering into this field. A loop, okay, is entering into this field. So what will be the direction of induced current in this case? So if it is entering, what will happen? Previously it was coming out here, no field. Okay, it is entering. So while entering, for this loop, actually cross magnetic field is increasing. It is entering into the loop. So all these questions we should solve in such a way that at that instant, okay, immediately after the process, what is going to happen? Definitely it will come here, it will go out. So our responsibility is not to find after this loop comes out of this. No, immediately after entering, what is going to happen? So instant effect, what is that happening? That is what we need to find. So when this is entering, while this is entering, okay, it is entering into a magnetic field area. So cross magnetic field will be increasing. Now according to Lenz's law, cross magnetic field should decrease. So what should happen? Dot magnetic field should increase. So dot magnetic field to increase, what should be the direction of current? Direction of current should be this. So what is this? Anti-clockwise. So this is the direction of current. What about this? Pause the screen and do yourself. Already we have seen that. What about this one? Pause the screen and do. Okay, done. Now this is going out. This is going out. So it was coming like a full cross magnetic field was present. Now when it is moving out, cross magnetic field is decreasing. So cross magnetic field is decreasing, then we should increase what? Cross magnetic field. So cross magnetic field means that is going inside. So this should be the direction of current. Okay. So clockwise. Clear? Fine. What about this question? What about this one? So here I is passing like this. So this I is constant. This loop is moving. Okay, this loop is moving actually in this direction. So what will be the direction of induced current? Okay, I is constant. Okay, pause the screen and do yourself. Okay, now see the answer. So current is moving like this. Magnetic field will be cross this side, dot this side. Okay, so cross magnetic field on this side, dot magnetic field will be on this side. Now what will be the direction of current here? Whether this cross magnetic field is increasing or decreasing. Okay, then only you will be able to say. See, we have studied near to the current carrying loop, the intensity of magnetic field will be more, or near to magnet, the intensity of magnetic field will be more. So as we move away, the intensity of magnetic field will reduce. So suppose here this is the intensity of magnetic field, then later the intensity of magnetic field will be this. Okay, so intensity of magnetic field will be decreasing as we move away from the wire, which is the reason for making magnetic field. So we can say that cross magnetic field is decreasing in this coil. So it will try to increase cross magnetic field which is going up. So this should be the direction of current. So clockwise. Clear? Done? Fine. What about this one? Okay, pause the screen, do yourself. This one, pause the screen and do yourself. Try to find the induced current, direction of induced current in this case. Okay, got it? Now current is running like this side cross, this side dot. So cross magnetic field here like this. When we go away, cross magnetic field will be, intensity will be reduced. The motion of this is going to be vertical. So when it reaches from here to here, is there any change in magnetic field? If it is moving in this direction, the magnetic field is reducing. When it is moving in this direction, there is no change in magnetic field. So no change in flux. So we can say that no induced EMF. Clear? So in this case, there is no induced EMF. It should be clear. Okay. There should be a change in area. There should be a change in magnetic field. There should be some change. Then only flux will change and EMF will be induced. Clear? Note it down. Okay, we will see another question. So here, dot magnetic field. Okay, so the question is this much. Okay, dot magnetic field which is increasing. Okay, the question is charge on plate A and B. So this is capacitor plates. Okay, very clear. So what will be the charge on plate A and plate B? Charge means not magnitude. Okay, positive charge or negative charge. Okay, seeing the options you will understand, right? So what will be the charge on A? What will be the charge on B? Positive, negative, neutral, can't say, or none. Any options can come. So pause the screen and do yourself. Okay, pause the screen and do yourself. Okay, right, done. Okay, shall I try? Now dot magnetic field increasing. So dot magnetic field increasing. Now what will this current will do? What the current will do? It will try to decrease the dot magnetic field by increasing cross magnetic field. Cross magnetic field means which is in this direction current should go. Cross means inner, inside. So current direction should be this way. This will be the current direction. So current direction is this, means positive charges will be moving in this direction, plus 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 plus. So current is moving in this direction. It means that negative charges will be coming to plate B. Clear? So that is how the charging of the plate will happen. Clear? Understood? Right? So we will move to next question. Okay. So this is a loop. Electron beam is coming like this. Electron beam accelerated. Okay, electron beam is accelerated. It is coming like this. Now you pause the screen and do on your own. Pause the screen, do on your own. Okay, done. Right, fine, we will see. So if electron beam is going like this, what will be the direction of magnetic field here? You took like this. If you have taken like this, that is wrong, because this is the direction of current. Okay, this will be the direction of current. So if this is the direction of current, okay, then this will be the direction of magnetic field. Okay, but this is electron, so we will have to take the current direction like this. So if we take the current direction like this, this will be the direction of magnetic field. So magnetic field here will be going inside. Okay, right? And this is accelerating. Accelerating means more will be coming, means the current will be increasing. Current will be increasing. Accelerating means current will be increasing. So cross magnetic field is increasing. Cross magnetic field is increasing. So what we will be doing? It will try to decrease cross magnetic field. For cross magnetic field, so for that, what this current will do? Dot magnetic field will be increased. So dot magnetic field means coming out. So direction of current will be this. So direction of current is this, means anti-clockwise. Clear? Okay. Now we'll come to this question. Now here electron beam is accelerated. Okay. Electron beam is accelerated. So electron beam, not electron beam, sorry, this is E plus beam. Okay, so charge plus charges are coming. This is E negative, E minus, so electron beam. This is E plus. So current is coming in this direction, accelerated. So current is increased. Current is increasing. Current is moving in this direction. Then the direction of magnetic field will be outside. So dot magnetic field. Dot magnetic field. So dot magnetic field is increasing. So we need to decrease dot magnetic field. So for that, cross magnetic field will be increased. Cross magnetic field means going inside. So current direction will be this. Correct? Cross magnetic field is this. So current direction will be clockwise. Clear? Take down. What about this question? So this is alpha beam. Alpha beam. Alpha beam means alpha particles are coming. Group of alpha particles. Alpha beam. Okay, continuous alpha particles are coming. So we can say that this is current. But V is constant. If V is constant, then this current is actually constant. Constant current. Constant current means B will be constant. Flux change is not there, so no current or induced EMF. No current or induced EMF. Okay, another question. A loop is here. A bar magnet is falling down like this. So generally anything which falls down will be moving with the acceleration due to gravity. Okay, so here whether this is less than or equal or greater than acceleration due to gravity, this acceleration. Okay, pause the screen, think and find your answer. Okay, so since this is moving away, what will happen? According to Lenz's law, north pole will be induced here, okay, by moving the current, and it will try to attract. So definitely a small force will be acting in the upward direction. Because of gravitational force, this will be coming, and because of this, G will be there. But now a small force will be acting upwards. So definitely acceleration will be less than acceleration due to gravity. What about this case? Here this is a loop, and this bar magnet is falling through this loop. So when it is coming like this, with the what acceleration it will come. Okay, so pause the screen and try yourself. What is the answer? So here when it is coming, again here also north pole will be induced, and it will apply a small repulsive force in the opposite direction, where Fg will be acting in this direction. So due to Fg only, acceleration due to gravity G will be coming. Since this force is applying upwards, definitely the net acceleration will be less than acceleration due to gravity. Clear? Okay students, so that's all about Lenz's law. Now you know Lenz's law, you know Faraday's law. Now both of them putting together, they can ask the magnitude of EMF, at the same time they can ask the direction of current also. Okay, so using Lenz's law concept, we can understand the direction of current. Finding the magnitude of EMF is not a very big deal. So both of them putting together, the question can be very conceptual. Okay, but you can do. Right, so practice this, try to find out more number of questions and try to do more practice. Okay children, so hope you understood the concept. Thank you, goodbye, good luck.